Okay, so this is our second class on quantum computing, and I am going to teach complex numbers today. Many of you are already familiar with this definition and concept, depending on the courses that you have taken before. Some of you have seen these numbers in high school or maybe in college in some, earlier math courses in calculus or discrete math or set theory and stuff like that. So today is more of uh, more of an overview of what many of you are already familiar with. We will make it, a little bit more advanced towards the end because we need to understand how complex numbers and quantum computing and quantum computers are related. Finally, okay. So we need these definitions in the beginning, as I mentioned on Wednesday. For the next 3 weeks, we are going to introduce some mathematical definitions and concepts before moving forward with, the quantum gates and architecture and quantum programming. Okay, so again, bear with me in the coming 3 weeks, and it's going to be less theoretical afterwards. So let's start with a brief recap. First of all, about quantum computers. Here I have a screenshot of IBM Quantum Systems. I think it's for a few years ago, but the technology, at least what we can see, has not changed significantly. So a quantum computer is basically a machine that performs calculations based on the laws of quantum mechanics, which governs the behavior of particles at the subatomic level. So here we are dealing with some qubits or quantum objects instead of bits. And the quantum computer at the hardware level deals with those qubits. And one thing that is very important, and it's a kind of motivation for the complex numbers that I'm going to introduce today, is this wave-particle duality concept that we have in quantum mechanics. There are so many excellent materials online. You can find very great educational videos on YouTube and other websites on these experiments. Again, how these experiments are performed, the setup and everything is far beyond the scope of this course, but I think watching them and learning more about these experiments will help you understand these things better. But what we need for this course is that, just the definition of wave-particle duality, which is a quantum mechanical concept stating that the fundamental entities like photons and electrons can exhibit both wave-like and particle-like properties. And this is very important because speaking of the wave-like properties of quantum objects, we need to somehow mathematically model them and then define some operations and gates to deal with them. And that's the main motivation for us to define complex numbers. Okay, so these are some motivations and recaps from what we learned earlier. And with that, let's start with some basic definitions in complex numbers. Any questions?
Yes, do we need to know about the wave function, that kind of things in quantum mechanics, or is just not important for this class?
We don't need to know that, but as I mentioned earlier, if you search for some additional resources on these topics, you learn more about those functions and experiments, but it's not needed for this course.
So is there any abstractive language to describe the quantum computing, like something like not a logical language, something like that, like a traditional computer?
We'll learn those things later, but only speaking of the mathematics needed for modeling the problems and dealing with qubits and those operations, we need to introduce complex numbers. So let's start with, the motivation behind complex numbers. So you're all familiar with polynomial functions, right? So do you have x to the 0? I mean, they have coefficients, but it's x to the 0, x to the 1, x to the 2, and then it goes to x to the n. And that's basically when you have the addition between them, it gives you a polynomial equation. And just working with this very simple polynomial equation like this, x squared plus 1 equals 0, very quickly you will learn that many polynomial functions like this do not have an answer in real number sets, right? So if you remember, we had this from the past. We're all familiar with natural numbers. They start from 1 and they go up 1 unit. And then we have whole numbers. We just simply add 0 to the natural numbers. And then we have integers, which add negative numbers. We have rational numbers, which can be written as the division of two integers. We only have one condition: the denominator cannot be 0. And if they cannot be written like that, then we have irrational numbers. When we put all of them together, we have the real numbers. But there is, as I showed you in here, there are some situations when the answer of equations like this are not in real numbers at all. And then this opens, a question. It raises a question whether we need another set which has the answer to all the polynomial equations. And for a long time, the definition of complex numbers was simply added in order to find an answer to the polynomial functions or equations that I showed you earlier. So it was basically a postulation. The equation that I showed you earlier, you just bring 1 to the other side, then you have x squared equals -1. And then you define that I have, an imaginary number. We call it I because it's imaginary. It starts with I. And we say that I squared equals -1. And therefore, I is root square of -1. So this, as I said, was only, a theoretical math for a while without any direct applications in any domains or any fields. And, mathematicians were very happy with just dealing with the theory and, not dealing with the applications. But after a while, again, speaking of the waves, and after that quantum computing, which works with quantum mechanic objects that have that wave-like properties, then the applications of complex numbers were more clear. So back to this definition, we just defined I as the root square of -1, and with that we can define a complex number. So the imaginary number is what I just showed you in the previous slide. A complex number has two components, right? The first component is the real number, and the second complex has this imaginary number in it. And then A in this case is just the real number, and B is another real number, which is the coefficient of that imaginary part of this complex number. Okay, so whenever we say imaginary number, we are only dealing with this I. When we say complex number, we have these two components. And your C, your complex number C in this set can be written as A plus BI, where A and B are two real numbers. Okay, and then B is this imaginary part. Okay, now that we have defined the imaginary numbers and also the complex numbers, then there are different operations that we want to run on these numbers. Let's start with an example. I'll go through some easy examples, and the harder ones I'm gonna pause and let you engage in solving those problems. So here you can see that we have two complex numbers, C1 and C2. And by the way, just back to this Venn diagram, you can see that all the real numbers are also complex numbers, right? If I just simply put 0 in here for B, then I'm meeting the second part, and therefore I only have the real number in here. So all the real numbers, integers, if you go, through the smaller circles in here, they are all complex numbers. So that's not a problem if you go backward. But when you're going from, natural numbers to the complex numbers, and especially real numbers to complex numbers, that's when you get to see that imaginary part. Okay, so here we have two complex numbers, C1 and C2, right? So C1 has these two parts, 3 minus I. So if you compare it with this definition, you can identify A and B in that setting. There are 3 and -1. And then C2 is 1 plus 4I. So again, this is A2, and 4 is your B2, right? And we want to compute C1 plus C2 and C1 times C2. So the addition is, pretty straightforward. You just simply add up the related parts. So you have 3 minus I plus 1 plus 4I. So 1 and 3, you just add them together. And then you have minus I plus 4I, which is 3I, and that's it. Okay, so addition or summation should be pretty straightforward. Related to that is subtraction, right? So in subtraction, you just simply, if you want to do C1 minus C2, you just multiply C2 by -1, and then you can just add them together. That's why we only focus on addition and multiplication. When it comes to multiplication, it gets a little bit complex, so please pay attention to what we do in here. We have C1 times C2. So again, I write these two numbers in here, and I start distributing these numbers like what we do in, algebra for real numbers. So I have 3 times 1 plus 3 times 4I minus or plus -1, -I times 1, and then -I times 4I. And some of it is easy. So 3 times 1, is 3. Here we have 12I. Here we have -I. And when I is multiplied by I, we have -1, right? That's exactly the main motivation here. I squared is -1, right? So wherever you see an I squared, you just simply replace it by -1. And therefore here, when you have -I times 4I, it gives you -4I squared, and I squared is -1, therefore you have +4 in here, right? So you add 3 and 4, and the rest of it, you just factor out I, you add these numbers, and this is what you get. So the final answer is 7, which is the first part of your complex number, and the rest of it, the coefficient of I is 11, and then you have your imaginary number. Okay, is this clear, or do you want me to repeat this before I move forward? It just gets more complex from here. So if there is anything that you don't understand at any point, please let me know. I would be happy to pause and repeat it if needed. And again, I remind you that this meeting is recording, is getting recorded. So if you want to go over it again, the material will be available to you later. Okay, so I hope that so far you're following me. We have a proposition here which is called fundamental theorem of algebra. And it says that every polynomial equation of one variable with complex coefficients has a complex solution. This is very important. And again, this is one of the main motivations for mathematicians to introduce and work on complex numbers, because what it's claiming in here is that every polynomial equation, okay, so once we define this big circle of complex numbers, we are sure that every polynomial equations with only one variable, though, with complex coefficients has a complex solution. So we are not missing anything in this domain, and we can find, all the answers to those polynomial equations. Okay, so far we only defined some basic definitions without going through, the algebra or the geometry of complex numbers. From here, in this subsection, we only focus on the algebra and, the operations that we run on complex numbers. So let's, look at the definition of complex numbers again. So what we showed in definition 1.1.1, which was in here, each complex number has these two parts, right? We have its real and imaginary parts. And another way of looking at complex numbers, which can make our life much easier, is that a complex number is basically a pair of two real numbers, right? So in this case, we are somehow, getting rid of that imaginary part I, and we are only storing A and B, which are the real numbers of that complex number. So if you have an ordinary real number which does not have that imaginary part, it means that the second component of this pair is 0 and you only have A. And if you have I as your imaginary number, then there is no real part and you're only dealing with the imaginary number. And since it's I, then its coefficient is 1 and you just store it there. So in this case, a complex number is nothing more than an ordered pair of ordinary real numbers. And order here is very important. That's why we present it by, the parentheses. If you remember from discrete structures, this indicates, the ordered pairs. So it's important where we put A and B, because the first part is related to the real part and the second part is related to the imaginary part. Okay, so with this new definition, let's just go over the addition and multiplication, which I explained earlier. And from that point, we are going to go a little further to look at some other properties of complex numbers. So with this new representation of complex numbers as ordered pairs, let's say you have two numbers, A1 and B1. This is the first complex number and this is the second one. When you want to add them, you just simply add the related components of the ordered pairs. So here you have A1 plus A2 in here, and then B1 plus B2 in here. When it comes to multiplication, it gets a little bit tricky. So in order to run this multiplication, you have A1 B1 times A2 B2. So you have A1 A2 and then A1 B2. But here you're dealing with that because it's an imaginary number, right? That's why you get to see that -1 in here. Then you have B1 A2, which is in here. And then you have B1 B2. Both of them are imaginary numbers. So when you multiply them, that negative is, canceled out. And that's why you see B1, B2 as as in here. Okay. And then you want to maybe test out the idea by just multiplying two imaginary numbers i's, right? So in this setting, we said that since imaginary numbers, they don't have that real part, then it's equal to 0. They only have the second part, and let's, multiply them together. So we just follow this rule in here, right? So we are going to have A1, A2, so A1, A2, which is 0, negative B1, B2, B1, B2, which is 1. And then you have A1, B2, A1, B2, 0, plus A2, B1, which is 0 again. So after multiplying them together, it gives you negative 1 and 0. So they don't have the imaginary part anymore. And it's just a real number, negative 1. And that is what we know by definition, right? We said that I squared equals negative 1. And that is what it's saying. And this is, again, another way of just restating what I said. So if you have a complex number of A and B, right? So you can say that this is the real part, therefore I have A and 0. This is the imaginary part, therefore I have 0 and B. And now I have the addition of these two numbers, right? A0 and B0. And then since this part is the imaginary part, right? You can just simply multiply it by 0 and 1, which is, basically your I. So this is how you can go from this ordered pair to A plus BI, which was, the first definition. So it's just showing that these are equal, and, whether you use this definition or this definition, as far as you follow the instructions that we have in here for addition and multiplication, it wouldn't matter. You can just simply convert them to each other. Okay, I have an example here for you, and I want you to work on it. So if you could take a screenshot of this page, I think it would be very helpful. You can also write it down if you cannot take a screenshot, whatever works for you. So in this example, we have two complex numbers, C1 and C2. Okay, so again, they're in ordered pairs. And what we want to do is to multiply them. And then what we want to do is to check their commutative and associative properties, right? So if you have something like this, by multiplication, you have these two numbers. So if you just simply go back to these roots, you have the instruction A1, A2 minus B1, B2, A1, B2 plus A2, B2. Okay, so you just simply, run it, and then this is what you get. Now there are some properties that are very important when it comes to addition and multiplication. We had these terms earlier in discrete math. So again, if you had this course with me or with some other professors, you may remember these terms. The first one says commutative, meaning that if you want to add two numbers, it doesn't matter if you add C1 and C2 or if you change the orders. Same thing with multiplication. They also hold this property. The other property is associative. It means that you can just simply change the order of addition or multiplication. So if you have parentheses over the first two, it means that first you run this addition and then you add the result to C3. Here it means that first you add C2 and C3 and then you add C1 and to that result. It doesn't matter, they're equal. Same thing with multiplication. Okay, so these complex numbers, they have these properties. They also have this property, same we have the same property in real numbers. So if you have C1 times C2 plus C3, you can just simply distribute C1. So you'll have C1 times C2 plus C1 times C3. So yes, these are the main properties of these numbers. For this one, I also have a proof of this property. For the previous one, I skipped the proofs, and we just agree that we have these properties. For this one, though, we can show that the right hand side and the left hand side are equal. So this is what I want you to work on, and it would be very straightforward if you just follow the instructions from the previous slide. So let's write this down somewhere or take a screenshot. So we want to show that multiplication distributes over addition for complex numbers. So if you have these three complex numbers, we want to prove this property. Okay, we just write it somewhere. And since I just taught the multiplication and you may not remember it, I'll go back to this slide. This is what you need as the reference, okay, for addition and multiplication. So what I want you to work on is to show that multiplication distributes over addition. And we just saw, these three numbers. This is what we want to show. Just go back to that definition and then show me that this property holds. And what you want to do is to work on the left-hand side first, and then you work on the right-hand side, and then at some point you'll see that the two are the same. Okay, let me pause here a little bit because this presentation is only includes the definitions and properties and stuff like that. And I want to make sure that you're following me and I'm just not going through all the slides, okay? So let me pause in here. I can also pause the recording, maybe for 2-3 minutes. I want you to show this property, okay? So again, let me go back to this slide. And with that, I want you to work on the two sides of the equation. Is it clear what you're showing, or do you want me to repeat it again? Okay, so Jeffrey, here. This is a property that we want to prove for complex numbers, okay? So it says that if you have three complex numbers, C1, C2, and C3, multiplication distributes over their addition, meaning that C1 multiplied by the summation of C2 and C3 equals C1, C2 plus C1, C3, okay? We know that this is, something straightforward for integers and real numbers, but now for complex numbers, we need to prove it. And we already have instructions on how to run a multiplication for complex numbers. So you just simply want to show them in ordered pairs, right? You have three numbers, C1, C2, C3. So you'll have A1, B1, A2, B2, C1, C2. A3, B3. And then you want to just simply use these definitions of addition and multiplication in order to show that property. Okay, so I'm going to stop in here so you can have a reference for addition and multiplication. And I want you to show that property of complex numbers. Is it clear for everyone now, or do you want me to clarify something? They are not available on Canvas now because, I have the questions and answers. So if I just simply show you the answers, then I think it wouldn't be as interactive as it should be. But right after this presentation, I'm going to post them on Canvas. Okay, is it clear what we... Yes.
Sorry, I cannot see your screen. Is it possible you can reshare your screen?
Okay, sorry.
I'm sorry.
I think I made a mistake. Thanks for letting me know. Okay.
Yeah, it's a bit messy, but so this was the statement we're trying to prove. So I started by just letting C1 be A1, B1, C2, A2, B2, C3, A3, where A and B are real numbers.
Okay.
So we started with the left-hand side, and I just substituted each C1, C2, C3 with the appropriate definitions. And then simplify. So we use the rule of addition. So just add A2, A3, B2, B3. And then this line is simplifying further by using the rules of complex numbers. From using the rule of multiplication for complex numbers.
Okay.
And then this line is just simplifying further. So then
this is what you have from the left-hand side, right?
Yeah.
Okay.
And then from here, I just moved on to the right-hand side. I kind of got stuck at this point. So I was like, let's just move on to the right-hand side and see what happens. So I did the same thing. Replace C1, C2, C3 with A's and B's. Use the rules of multiplication and addition to simplify. And I think if I had continued, I would have ended up with the same terms here and here.
Okay, so could you verify that the terms are the same, or were you in the middle of showing that?
Yeah, I was. I think I just had to combine all the all the real numbers and all the complex parts, and they would have ended up being the same.
Yeah, I think something with the right-hand side after multiplying the numbers, I think something is a little. Yeah, I think that I don't see the real part and the imaginary part, but good job. I mean, this is what you should have done. Maybe for the right-hand side, you needed more time to finish it, but good job. Could you stop sharing your screen? I think Elias. Oh, okay. You typed the entire thing here. Thank you, Alan. Okay, I see Elias. It's okay. So I appreciate typing the entire thing, but it would be a little hard for me to verify that. So let me share the answer with you all, and then you can see if you could run the math correctly. So let me get back to my slides. Okay, so let's take a look at it together. So this is very much similar to what Alan just explained. So we have the left-hand side, these numbers. We start off with what we have in the parentheses. So we have these two numbers. We add them up according to the rule of addition that we had earlier. And after that, we multiply this number, A1, B1, and this number, right? So we have A1 times this minus B1, and this is this is the first part, and this is the imaginary part, right? So if you want to just verify that, again, we can go to the instructions in here. right? When it comes to multiplication, we have A1, A2 minus B1, B2, right? So if we go in here, so this is A1 and this is our A2 minus B1 times this is our B2 and so on. So you just simply follow that. And instead of B2 and A2, we have two terms. So that's the only thing that you need to take care of. And then for the right-hand side, right? When we have this C1 times C2 plus the C1 times C3, we just follow those instructions again on multiplication. So this is what we get in here. We need to have these two components. So this is what I think was missing in Alan's solution, but basically this is where you get. And then you can verify that these, what you see in 121, and then what you see here in 124, they match. Right. So just simple math, simple algebra, nothing complicated. You just want to be careful about those rules because as I showed you with complex numbers, especially when it comes to multiplication, it can get a little tricky. As I mentioned earlier, a subtraction, it's just, an extension of addition. So instead of, subtracting C2 from C1, you can look at it from, the addition point of view. So you have this number minus this. So you just simply, find the difference between A1 and A2 and then B1 and B2, right? It's like addition when you multiply -1 to the second number. When it comes to division, similar to multiplication, it can get a little tricky. So let's look at it together here when we have the division of two numbers, okay? So let's say X and Y are the results of, or you can say that they are the results of this division, right? So you have the division of two complex numbers, A1, B1 in here, and then A2, B2 here in the denominator, okay? So let's work on the math together. Again, nothing complicated. It's just basic algebra of the complex numbers. So what you can do is to say that A1, B1 is basically the multiplication of X1, XY times A2, B2. We know how to multiply these two numbers based off of what I just showed you, right? And if you do the math, A1 will be the first component, and then B1 will be the second component, okay? So then what it means is that A1, A2, you can calculate A1, A2, and then B1, B2, right? You currently have A1 and B1 in here. So you can, based off of that, just find A1, A2, and then B1, B2. And then if you add them together, this is what you get, right? A1, A2 plus B1, B2, you just add these right-hand side terms. So these two terms basically cancel out, and you only have A2 squared plus B2 squared. So with that, X will equal A1 plus A2 plus B1 times B2 divided by this number. And you can do the same thing for Y, right? So this is what you got from here, right? So you can do the same thing, by, multiplying, one term, this term by -1. In that case, those with X terms will cancel out. And you can find the value of Y. And once you have X and Y, just, returning to the first definition, you have the division of those two numbers, right? So it's going to be this, which is your real parts, and then this one, which is your imaginary part. So this is how you can divide, two complex numbers. And then another thing that is very important is the modulus, or as we shall see later, the length of a complex number. Okay, so you are familiar with this notation. We again had it earlier in discrete structures. So you are basically finding the absolute value of a number when when we are using this notation. So it's going to be the root square of a squared, and we are dealing with the positive part of it, right? Because it's absolute value. So if you want to find the absolute value of a complex number, in this case, you just extend that definition, right? So you find a squared plus b squared, and that's it. So if you have a complex number like this, its modulus, and as we shall see later, the length of the corresponding vector will be, we have this positive sign, just to make sure that we are not, messing up with the signs. And then we have 1 squared, or a squared, plus b squared. And b in here is -1. So -1 squared is 1. So it's going to be square root of 2. Here is a definition. I know we just showed all of these features and properties for complex numbers. Let's review them together. We showed that addition for complex numbers is commutative and associative. We showed that multiplication also has these two properties. Addition has an identity 0, 0, meaning that if you add 0 and 0 to a number, it will be similar to the original number. It doesn't do anything in here, so we say it's identity. With multiplication, its identity is 1 and 0. We showed that multiplication distributes with respect to addition. This is, the example that I paused and let you prove it. We showed how subtraction and divisions are defined. The only exception for division is when the divisor is 0. Otherwise, you can always define them. And apparently, there is a relation between subtraction and addition, division and multiplication. So whenever we have a set which has all of these 8 properties and operations, or a set with operations satisfying these properties, we call it a field. And complex numbers are a field. Real numbers are also a field. You can show that they have all of these properties. But what is very unique about complex numbers, as I showed you in a proposition in here, this is a property that real numbers do not have, is that every polynomial equation of one variable with complex coefficients has a complex solution. So we are sure that whatever polynomial equation we have, their solution is in the field of complex numbers. We don't have this property for real numbers. So although they are a field, they do not satisfy that property, and that's why complex numbers are very valuable and are very important sets for mathematicians. Okay, another thing that I introduced is about changing the signs of a complex number. So when you have a complex number, again, we are dealing with a pair of, with an ordered pair, right? We have these two parts. So when I say we want to change the sign of that number, you may ask, okay, which part? Do we want to change the sign of the real part, the imaginary part, or both of them? Okay, so if you want to change the sign of both components, you just simply multiply that complex number by -1 and 0. There is a proof for that. I'm not going to show it in here. Just accept that this is how it works. when it comes to changing the imaginary part only, since it's really important and it does have some implications later, it does have a special term. It's called conjugation. Okay, so if you have a complex number C equals A plus BI, then its conjugate, which is shown as C bar, is equal to A minus BI. So you only change the sign of the imaginary part. And we say that two numbers related by conjugations are said to be complex conjugates. So C and C bar in this case are complex conjugates. And the third situation was the case that you only change the sign of the real part, but not the imaginary part. So in that case, you're changing C to negative C bar. So by multiplying C bar by -1, it means that you are changing the sign of the real part and changing the sign of C bar, meaning that you are getting back to the original number for the imaginary part. So in this case, you're only changing the sign of the real part, but it doesn't, since it doesn't have, any important implication, then we don't have a particular name and we don't really deal with that. So I would say the most important part in here when we are changing signs is when we only change the sign of the imaginary part, and for that we have a special name. It's called conjugation. Okay, is it clear in here? Okay, hopefully yes. And with that, we are going to take a look at the geometry of complex numbers. So let me just review everything very quickly. I started off by showing some basic definitions and motivations. I mean, how we decided, the mathematicians decided to introduce imaginary numbers. What was the main motivation for them? Then we looked at the algebra of complex numbers. So we looked at, addition, multiplication, subtraction, division. We looked at some properties together, and we defined conjugates, we defined fields and stuff like that. We stopped there, and now we are switching over to the geometry of complex numbers. And you can see that the geometry and algebra of complex numbers, they somehow complement each other. They are not, very separate. Geometry helps us visualize the complex numbers using vectors. And with that, we can, establish a better insight about what these numbers are and how we deal with them. Okay, so let's take a look at the geometry of the complex numbers. So we introduced earlier that each complex number has two parts, the real part and the imaginary part. And if you work on the complex plane or the Argand plane, in that case, you have an x-axis, which is showing you the real numbers, and then the y-axis, which is showing you the imaginary numbers, okay? So we have something similar in the Cartesian plane when we have x and y, right? So we're already familiar with that space. In this case, though, we have real and imaginary. This is how it differs. And with that, we'll be able to show each imaginary number with its corresponding vector, right? So we know that A number, which is related to the real part. We also know the B value, which is related to the imaginary part. So we can find that point in here and then find the vector in that space in order to point to that number. Is this clear to everyone? Because from here, I'm going to add more definitions in this space. So I want to make sure that you understand what a complex plane is. Very good? Okay, then let's move on to the next slide. And here I define the length of the vector. So let's say that you have a vector, you have a complex number C, 3 plus 4i. So again, on the x-axis, we have real numbers. A is 3, so I have 1, 2, 3, and then 4i. So I go to the positive direction. This is my 4i, and this is the vector connecting the origin of my complex plane to that number. Okay, so this is my vector, and if you remember earlier, we had the definition of modulus in the algebra of complex numbers. So let me show that to you very quickly. You understand that the modulus of a complex number is in fact the length of the corresponding complex number in the complex plane. So earlier I showed you in here that if you have a complex number C, you can calculate its modulus, and that's the square root of a squared plus b squared, right? Now we have a better idea about what that modulus is given this representation in the complex plane. So if you have a vector like this, 3 and 4, if you want to find that the length of this vector, you just simply find, this hypotenuse of that triangle, right? So it gives you the root square of 4 squared plus 3 squared, which is 5. Okay, so far so good. Yeah. Okay, so addition and subtraction, hopefully you remember, this from linear algebra when we define vectors. So if you have two vectors, C1 and C2, if you want to add them, this is what you get as their addition. Another way of looking at it is that if this is C1, you just copy C1 to the end of C2. So C2 plus C1, it gives you this. And if you're subtracting C2, then you have to change its direction. So instead of going this way, negative C2 goes this way, right? So again, if you have a copy of C1 in here, and this is your C2, so this is going to be the subtraction. So this is the addition following the parallelogram rule, or just the addition rule, and this is their subtraction. Okay, now it gets...
excuse me.
Yes.
Is any vector representation for the multiplication?
Oh, I'm going to introduce that. Yeah, you just need to wait a little bit. Yes. Okay, so we can go from Cartesian space to the polar or Cartesian representation to the polar representation and vice versa. So when we are in the Cartesian representation, it means that we are dealing with that ordered pair of A and B, right? Whereas when we are in the polar representation, we are dealing with rho, which is, that's the length of that vector or modulus of that complex number. We call it rho, and theta, which is the angle between, that vector and the x-axis, theta. Okay. So we have, the conversion between the two spaces. So you can go from Cartesian to polar space. So in this case, your rho or the modulus is basically, the root mean square of a squared plus b squared. And then theta is the invert of this tangent. So you have b divided by a, and then you find tangent inverse of that number. Okay, so this is how you find rho and theta. And again, you have this, if you can call this A, and B. So this is your vector, right? And then you can try to find that theta, and rho is basically the length of your vector. And then if you want to go from a polar to Cartesian, so if you have theta and rho and you want to identify or you want to calculate A and B, then this is how you do the math. So A will be rho times cosine of theta, and B is rho times the sine of theta. So depending on what you have in the problem and how you want to convert them, you can either use this formula or this formula. And this is, one example. For example, if you have a complex number like this, if you are asked to find its polar representation, so you're going from Cartesian to polar, right? Then you need to find rho first, which is, the modulus of this number, and then theta, you find this tangent, this value. You need to know a little bit of trigonometry. I mean, in quizzes or exams, I can give you these numbers, but hopefully you remember, the very, famous numbers. So pi divided by 4 has this tangent value of 1, and this is how you calculate it. Okay, so just bear with me before I define the multiplication. So what is very important in here, and I have just 2 more slides and then I'll be finished, 2 or 3 slides. So this gives us a better insight about, we are connecting the dots, right? How this can be related to, the quantum world, and, how these things are making sense when we put everything together. So speaking of the polar representation, and when you are in the complex space, you see that, when you have a circle right like this, when you are in this center and this circle has this radius of r, right? So all of these points, they have the same radius, or in other words, they have the same modulus. They have a fixed modulus, let's say it's 1 in this case. They are only different by this theta, which is adding the phase to this definition, right? So it's somehow similar to your watch. If you have, the needle moving, right? So it's you're basically adding the importance of time or phase to your calculations. With the same modulus, you're adding the phase. And this is another way of interpreting complex numbers. You can say that a complex number is the magnitude. So this magnitude is basically that rho or modulus and a phase. So with that theta, you can show the phase of your system. And with all of these, now we are able to define the multiplication of 2 complex numbers in, using their geometry. So if I have 2 complex numbers, rho 1 and theta 1, and rho 2 and theta 2, this is their polar representation. Their multiplication has 2 parts. The first part is rho 1 times rho 2, so you're just multiplying their modulus. And the second part, you add their phases. Okay, this is how you multiply 2 complex numbers using their polar representation. So for example, if you have these 2 complex numbers, I have this beautiful example. Unfortunately, we don't have time to go through this, so I'm just simply going to share this with you after this class. So if you multiply them, you have 1 plus I and then negative 1 plus I, right? We know the rules of multiplication, so you just simply apply them, and this is what you get, right? And if you go by so this is what you have from the Cartesian representation. And if you go by the polar representation, right, this is how you convert those numbers into their polar representation. And then you apply the multiplication rule that I just shared with you. So it gives you 2 and pi as their multiplication. So when you revert it to its Cartesian coordinates. So you see you have 2 and pi, right? So it's your rho and theta. When you have your rho and theta, I just showed you how you can, when you have rho and theta, this is how you can convert them to A and B, right? So this is what you do, and you get -2 and 0, meaning that it only has the real part and its value is -2. And this is exactly what you get here if you just simply go with the algebra. Okay?
Yes,
Okay.
Hold on. What's the general form of the multiplication? Because the example it covers.
Sorry, let me stop recording first. It's 2:56. We're running a little late, so I'm going to stay here for a few more minutes. I again stop sharing my screen. Let me stop recording.